The ensemble average of a system quantity at time t is the expected value computed across all parallel realizations at that instant. The time average is computed along a single trajectory over a period t. These two quantities are defined differently and may not coincide. Their equality is a property of the system's dynamics, not a general law. In ergodic systems, the time average converges to the ensemble average as t grows without bound. In non-ergodic systems, the two averages diverge, and using one to predict the other produces systematically incorrect conclusions. A system is ergodic if its time average converges almost surely to its ensemble average in the limit of long observation. This is a structural property of the dynamical system. It depends on the equations of motion, not on the distribution of the perturbations. In an ergodic system, a single long-running trajectory samples all regions of state space with the correct frequency. It behaves like a representative sample from the ensemble. In a non-ergodic system, individual trajectories do not sample the state space representatively over time. The failure of ergodicity means that ensemble averages cannot be used to predict the outcomes of a single system evolving through time. Additive dynamics accumulate increments. The state at time t is the sum of all past increments. Under additive dynamics, the time average and ensemble average coincide. The system is ergodic. Multiplicative dynamics compound factors. The state at time t is the product of all past multipliers applied to the initial state. Under multiplicative dynamics, the ensemble average can grow without bound while the typical trajectory decays toward zero. This divergence between ensemble and typical behavior is the defining feature of non-ergodicity in multiplicative systems. In multiplicative dynamics, zero is an absorbing state. Once the system state reaches zero, no subsequent multiplier can restore it. This makes ruin irreversible. Once the trajectory crosses the zero boundary, no return is structurally possible. A large ensemble average does not protect against ruin. It can grow because a small number of trajectories are scaling dramatically, while the majority converge to zero. The ensemble average is dominated by the extreme positive outcomes, not by the typical trajectory. Designing for ensemble optimality in multiplicative systems is therefore not equivalent to designing for individual system survival. The time average growth rate of a multiplicative system is determined by the geometric mean of its growth factors. The geometric mean is always less than or equal to the arithmetic mean, with equality only when all factors are identical. A system survives in the long run only if its geometric mean growth rate is positive, meaning each unit of time leaves the state on average larger, multiplicatively. A system with a positive arithmetic mean growth rate but a negative or zero geometric mean rate will approach the absorbing state with probability 1. Engineering for long-run operation must use geometric growth as the design metric, not expected value. In ergodic systems, ensemble statistics correctly predict what an individual system will experience over time. The two are interchangeable by construction. In non-ergodic systems, the same tools produce misleading results. Positive expected value does not imply survival, and high ensemble average does not protect against ruin. Applying ergodic design tools to non-ergodic systems systematically underestimates the probability of reaching the absorbing failure state. The relevant performance metric changes. In ergodic systems, it is the expected value. In non-ergodic systems, it is the geometric mean growth rate. Determining which class of dynamics governs a system's operation is therefore a prerequisite for correct design specification.